This video is about indefinite integrals using substitution. For our notes, we'll say this as a definition. Many functions do not fit with the antiderivatives we already discussed. We're in the context of calculus where we've already understood an antiderivative and an indefinite integral, but we've only done really basic examples at this point. Hence, we may need a new strategy to address them. And this strategy is called substitution. It's often referred to or called u sub, since the variable u is often used in it for the substitution. Our main key will be this. We'll usually want to let u represent some part of the integrand whose derivative is also part of the integrand, perhaps off by a constant. There is some variation in this, as we'll see. We'll try to include many examples in this video to show some different cases, but generally speaking, this is our go-to as far as knowing what to let u equal for the substitution. Our first example is to find the integral, the indefinite integral, of x squared times e to the x cubed power dx. You'll notice this function in the integrand does not fit any of our basic antiderivatives that we already know as we've been working with. So here's where we're going to use a substitution to try to get around it. We're going to let u, that's our substitution variable of choice here, we're going to let u equal the exponent of the base e. So we're going to say let u equal x cubed. Now let's see how this comes together in fitting with our notes above. I then would like to take the derivative of this u equation, which means we'll say du dx equals 3x squared. We're just taking the derivative with respect to x, du dx, and so this is just the basic power rule here, so 3x squared. But then we also would like to start to spot the ways we're going to replace or substitute all these u values in for our original integrand. If I multiply both sides of this du dx equation by dx, I would end up with du equals 3x squared dx, which is getting better. So notice that we're trying to replace our original integrand, and we're getting one little piece at a time. Notice there's an x squared and a dx in our du equation now, and that could replace the x squared and dx that is in the original. But notice that we're off by this constant of 3. There's no 3 showing up in this original integrand. So we're going to just divide both sides of this du equation by 3 to end up with 1/3 du equals x squared dx. So now the x squared dx will be replacing those two factors as we've already underlined in our original integrand. But then we have this extra 1/3 in front of the du that's going to be replacing it. Well, that's an easy fix, as we'll see next. So let's go ahead and rewrite our original integrand. We had the integral of x squared dx, but remember, those two factors are going to be replaced by 1/3 du. That's just a direct replacement from what we just said. 1/3 du is x squared dx, and so those show up instead. But we have to be a little more careful on how we write this. Recall that a constant, like this 1/3, could be written out in front of the integral, and we'll go ahead and put it there just for organization. The du will end up near the end as the variable of integration. And then everything else, of course, we have to still represent everything in the original integrand. We had this e to the x cubed there as part of our function. Well, we're going to keep that, but write it as e to the u, since we let x cubed be represented by u. Now what you'll notice is that we have an integrand that's much simpler, and yet it's doable with our basic antiderivatives. So we can rewrite this as 1/3 and then e to the u plus c. That's just doing a basic antiderivative with that function. And then we want to replace u with what we had let it equal so that we end up with 1/3 e to the x cubed plus c. We're just replacing u with the x cubed, and this will give us our final answer for this indefinite integral. Notice the plus c that has to occur for the general constant, as we've already seen. Our second example is the integral of sine of t times the square root of 1 plus cosine t dt. Now in this case, again, we're looking for part of the function whose derivative is also part of the function, but it's possible to say, well, wait a minute, there may be a couple options of that because the derivative of sine is cosine, or similarly, the derivative of cosine is negative sine, so that's not too far off either. But ultimately, what we want to do with our substitution is make this integrand as simple as possible. So we're going to try to replace the ugly part, or the part that's a little more complex, which means I'm going to let u equal what's underneath this root sign. So if we let u equal 1 plus cosine of t, that's what's underneath the square root. Now notice our variable of integration here is t, and so we'll find next du dt, which will end up being negative sine of t. The derivative of cosine is negative sine, and then we can multiply both sides by dt like we did before to end up with du equals negative sine t dt. Now we're trying to make some replacements here, and notice that sine of t and dt are two factors that could be replaced in our original integrand. We are off by this constant of a negative sign, but if we divide both sides of our du equation by -1, we end up with negative du equals sine of t dt, where the sine of t dt is what's going to get replaced, and it gets replaced by this negative du. So let's go ahead and rewrite our integral, but this time I'm going to replace the sine of t dt, as we just mentioned, by this negative du. Well, I'm going to throw the negative out in front and the du at the end. Remember, the negative is like a -1, that's just a constant which could be put out in front of the integral. The du is going to show up, but at the end for the variable of integration. The only thing left is what's in this middle of this original function, which would end up being the square root of u, since we let u equal the 1 plus cosine of t already. So the whole idea with substitution is that by the time you make your substitution, every part of the original integral needs to be represented by something in this new substitutionary form of it. So again, let's reiterate that the sine of t and the dt, those got represented or replaced by the negative du. So the negative sign we have and the du that we have, those are replacing the sine of t and dt. And then you could say that the square root of 1 plus cosine of t is represented by this square root of u we have in the middle. So every part of the original integrand is still present, just represented or substituted with different values. And the whole point of doing this is not only that everything's represented, but now it's represented by a simpler looking integral. If we understand this integral really to be equivalent to negative integral of u to the 1/2, that's square root of u, du, then we can just use our familiar power rule going backwards antiderivative for this one and end up with negative, and then it would be u to the 3/2. We're adding 1 to the power, but then we would divide by that power of 3/2, and then we would have to say plus c for our constant of integration there. And then we can simplify this, of course, more. First of all, this 3/2 in the denominator could be kind of flipped up with a reciprocal, so we end up with negative 2/3 on the same level here, and then we have u to the 3/2 plus c. But then, since we already did the anti-differentiation here, we also want to go back and replace u with what it was originally set to be. So we'll rewrite this one more time as negative 2/3, and then I'm going to put where u was in parentheses here, and recall that that was really 1 plus cosine of t. So we have negative 2/3 parentheses 1 plus cosine of t, but then those parentheses are to the power of 3/2, as we saw with our antiderivative, and then we'll have plus c. So ultimately we have our antiderivative here using a substitution. Our third example is the integral of secant squared of 2 theta d theta. Now again, we're looking to let u represent some part of this function whose derivative is also part of this function, but sometimes that's not always super clear. If you look at this one, you'll see a secant squared. You may recognize that as one of our common derivatives. The derivative of tangent is secant squared. That actually should help us using or doing the antiderivative, but that function's derivative is not here, or in other words, you wouldn't say that we're going to let u equal tangent because tangent isn't in the integral at all. So what we're going to have to say here is let's let u equal the inner part of this trig function, the 2 theta. Now this may seem too simple or just trivial, because then if you proceed with the derivative of u with respect to theta here, we'll end up with du d theta equals 2, which almost seems too simple, but let's go with this for a little bit. There wasn't really much else in this integrand. If I multiply both sides by d theta, of course, I'll end up with du equals 2 d theta. That's going to help us replace the d theta that we have in our original integrand here. Notice we don't have a 2, but remember, a constant can be accounted for pretty simply. If I just divide both sides of this du equation by 2, I'll end up with 1/2 du equals d theta. Of course, the d theta is going to get replaced, and so our new integral, which I'll put on the side over here, is going to be the integral of, now we have secant squared that's remaining there, hasn't been touched yet, but now it's secant squared of u, because that's what we let u equal, the 2 theta there. And then the d theta, we already mentioned, that gets replaced by 1/2 du. Well, I'm going to put the 1/2 out in front and the du at the end, so that our new integral is 1/2 times the integral of secant squared of u du. But then, as mentioned, this uses one of our standard or basic antiderivatives. We'll rewrite this as 1/2, keeping the constant out front. The antiderivative of secant squared would be tangent, and so we'll say tangent of u, but then plus c, and then simply replace u with what we had set it equal to, giving us a final result of 1/2 times the tangent of 2 theta plus c. Our next example is the integral of y squared times the quantity in parentheses of 4 minus y cubed, but then those parentheses are raised to the 2/3 power. If we look around for some part of this function whose derivative is also part of this function, I think we'll be able to set u equal to what's inside the parentheses, which is the 4 minus y cubed. And let's first of all consider why we might have picked that. And that is, if you take the derivative of this function, you're going to end up with a 3y squared, negative 3y squared with this second term with the y cubed there. So understanding that this derivative will involve a y squared, and we have a y squared as part of our integrand, that can help motivate us to try it this way. Let's go ahead then and find du dy. This time our variable of integration is y, and that will end up being just negative 3y squared from our u equation previously here. And then we could go ahead and multiply by dy on both sides, and let's do two things at once here. Notice we're off by a constant. You can spot that we have a y squared we're trying to replace in our original integrand, and we have a y squared in our du dy equation here, but we don't have this negative 3 in the original, so we'll end up dividing both sides of this by negative 3. At the same time, we're going to multiply by dy on both sides, which will end up giving us a negative 1/3 du equals y squared dy. That's just doing a couple algebraic steps at once with this du dy equation. But again, now this y squared dy will go back and replace the y squared and the dy from the original integrand. Of course, inside the parentheses we have just u, which will be convenient as well. Let's go ahead now and rewrite this integral originally given, but now we're going to rewrite it as the integral of, I'm going to put the negative 1/3 out in front for our constant, and then the du at the end. That's taking care of our replacement values here. And then we're going to replace the y squared dy with those, so that's all done. The only thing left would be in parentheses u to the 2/3. Remember, the 4 minus y cubed that was originally in the parentheses is what we set u to be. So now we're just writing the u. Notice we only have u's and du's in our new integral, and also notice that everything is represented. The original value in the parentheses is now replaced by the u. The 1/3, negative 1/3 du is replacing the y squared dy, and so everything is set to go. We'll go ahead and apply an antiderivative here and rewrite this as negative 1/3, and then it's going to be u to the, add 1 to the power, so that'll be u to the 5/3 divided by 5/3 plus c. Okay, let's go back around and continue this here. Simplifying it a bit would give us negative, if I flip this 5/3 up and over, I'll end up with 1/5, because the 1/3 will cancel with the 3 that was underneath the 5 when I flip it over as a reciprocal. And then I'll have u to the 5/3 plus c, but remember, we don't leave u in the problem like this. We're going to replace it and end up with negative 1/5 times 4 minus y cubed in parentheses to the 5/3. That's just replacing the u value that we had set originally, and then plus c. Let's try a next example. This one is the integral of e to the negative 5r dr. You'll notice in this example that there isn't a whole lot going on with the function in the integrand. It's just e to the negative 5r, and remember, we're looking to replace part of it, but we're also looking to let u be something whose derivative is also somehow within this integrand, perhaps off by a constant. Well, if we try letting u equal negative 5r, that almost seems a little too simple, but think about this. The derivative of negative 5r would simply be negative 5, which is just a constant. Now, we don't see that constant in the integrand here originally, but remember, a constant is easy to fix if we're off by it. So let's go ahead now and take the derivative of our u equation, which will give us du dr. We do it with respect to the variable of integration given here originally. So du dr is simply going to be negative 5, as we mentioned. If I multiply both sides by dr, I'll end up with du equals negative 5 dr. Now, that's not part of our original integrand, at least completely. The dr is, but if I just divide by negative 5 on both sides, I'll have negative 1/5 du equals dr, which means I can replace the dr with the dr, and that will end up using the negative 1/5 du in its place. So if we rewrite our integral, we'll end up with e to the u, since that's what we let u be originally here, this negative 5r, and then the dr is getting replaced with this negative 1/5 du, but the negative 1/5 we can just put out in front as we've been doing, and the du we can put at the end. Then we'll go ahead with the antiderivative of e to the u with respect to u, which is a simple one. This will just be the negative 1/5 constant stays out in front, and then the antiderivative is just e to the u, and we could say plus c. If we go back and replace u with what it was, we'll end up with negative 1/5 e to the negative 5r plus c. Let's try another example. This one is the integral of, it's a fraction where the numerator is the sine of the square root of x, and the denominator is just the square root of x. And this is all dx. Now we're looking to integrate this, and obviously this doesn't quite match one of our basic antiderivatives that we know already. Part of it might. I mean, there's a sine in it, and there's a square root of x in it, but this combination of them doesn't quite match any standard antiderivative. So we're going to have to use a substitution here, and recall that we want to let u equals some part of this integrand whose derivative is also part of the integrand, perhaps off by a constant. Notice that if we let u equal the square root of x, then we could say du dx, when I take the derivative of this u equation here, is going to equal, and then you may recall the derivative of the square root of x, which you could write as x to the 1/2, okay, but summarized, the derivative is 1 over 2 square root of x, as we've seen before. And that's actually looking a little bit better. Now we want this to line up a little more closely with what we're trying to replace in this original integrand. And to do so, I'm going to do two steps at once, kind of like we did here previously, which is I'm going to multiply both sides by dx. And since we're off by this constant of 2, I'm also going to multiply both sides by 2. There's this extra 2 in the denominator here that doesn't quite show up in our denominator in the original integrand. So I'm going to multiply both sides by 2 and by dx. This will result in 2 du equals 1 over the square root of x dx. That's just kind of doing two multiplications in one step there. But now notice that the square root of x in the denominator matches the square root of x in the denominator of our original problem. The dx will also match it, and then this numerator sine of square root of x will be represented, of course, just by u. So let's rewrite this integral with a 2 out in front. That's the constant that's going to be replaced, as we saw here, with the du at the end. Okay, so that's now accounting for all of the items we replaced directly, but then we'll have to write sine of u, since that's also what's left. So to be clear, this 2 and the du is replacing the square root of x and dx, and then the sine of u is representing the sine of the square root of x, which means everything in the original integrand is represented. We need that to be true, and yet it's giving us a simpler integral to work with. So let's go ahead and rewrite this as 2 times the antiderivative of sine of u would just be negative cosine of u, and then we'll say plus c. And then of course we want to replace u with what it's equal to, so we'll rewrite this as negative 2 times the cosine of the square root of x plus c. Our next example is the integral of a fraction where the numerator is z squared and the denominator is z cubed plus 1. This is all dz. And so we want to use some kind of substitution, knowing that this doesn't quite match one of our standard integrals. You may try to work on simplifying this expression algebraically. Be careful when you have two terms in a denominator and one term in the numerator. There's not actually a whole lot of simplifying you can do with that. There's a common mistake done with that, where often students will try to split this up and make z squared over z cubed or z squared over 1. That does not work. That only works to split a fraction when it's reversed, where you have your two terms in the numerator and your single term in the denominator. So just be careful with that. Rather, we'll spot part of this function whose derivative is also part of this function, again off by a constant. If I let u equal this denominator of z cubed plus 1, then we could say du dz will end up being 3z squared. Now again, notice that 3 is not part of our integrand originally, but the z squared is. So we'll go ahead and proceed with what we've been doing here, which is kind of rearranging to make it fit better. If I multiply both sides by dz and divide both sides by 3, I'll end up with 1/3 du equals z squared dz. Now notice the z squared dz is going to replace those exact pieces in our original. So let's rewrite this as the integral of 1 over u, which will take care of the z cubed plus 1. But then we need this extra 1/3 constant represented, and then we'll put our du at the end. So this one got simple pretty quickly here. Notice everything is represented in the original. That's what we need. And furthermore, this is an antiderivative we can handle. So we'll rewrite this as 1/3, keeping the constant out front. The antiderivative of 1 over u du, as you may recall from our basic antiderivatives, would be the natural log of the absolute value of u, okay, and then plus c. Alright, so we'll go ahead then and replace and make this 1/3 times the natural log of the absolute value of z cubed plus 1. That's what we had originally set for u. And then plus c, which will take us to our final result. Let's try another example. This one is the integral of sine of x times the sine of cosine of x dx. If we let u equal the cosine of x, that will help simplify our function, and it's also true then that du dx will be negative sine of x, which is useful. That's within our function. So we could then say that du equals, in fact, if I divide both sides by negative in the same process here, I'll have negative du equals sine of x dx. Well, that's good news because the sine of x dx could replace a major portion of this function. If we rewrite this as the integral of, now I'm going to put the negative out in front that we have, and then the du at the end that we have. Those are both going to step in for the sine of x dx, as we've already seen, which means all we have left is the sine of u representing the original portion of our function. Now we can proceed with the antiderivative. Now this negative that we threw out in front, you could almost put that in with the sine. That might be a little more familiar. The antiderivative of sine is negative cosine, and so this negative sign is going to cancel with that extra negative we get. So we'll just write this as cosine of u plus c, the antiderivative of sine, with this extra negative canceling the negative in the antiderivative here. So then we'll replace u with what we knew it was. So we have cosine of x plus c. Our next example is the integral of x times the square root of x plus 2 dx. Now in this case, we're going to try letting u equal what's inside this root, so x plus 2. Remember, we want to let u be something whose derivative is also part of this function. Well, this example has a little twist to that. See, if I just let u equal x plus 2, then I can go through the usual steps of saying, well, okay, then du dx is simply 1. The derivative of x plus 2 would just be 1. And that, of course, is just a constant, is part of our original function. The question is this replacement going to help with anything? Because we could also multiply both sides by dx, in which case we get du equals dx. You may start to wonder, well, is that a useful substitution? Isn't that just trivial? Like, we're just changing letters. Does that really do anything? But let's go ahead and notice that the du is going to replace the dx, which only accounts for the dx in our original integrand. That leaves a whole lot left to work with. Furthermore, if I'm going to replace dx with du, I need to have only u's in my integrand to match my variable of integration. So what we're going to have to do is take this original u equation that we had set up here, and we're going to solve it for x instead. If I just subtract 2 from both sides, I'll end up with x equals u minus 2. That just comes directly from the original u equation we had set up, which means now I can replace x's with u's. That's the whole point of that. Let's go ahead and rewrite this integral and do just that. Instead of the x that I see in my original first factor, we're going to replace that with a u minus 2 as we just discussed. Then we'll have the square root of u, and then we'll have du. So everything is getting replaced as we were expecting or hoping it to be, but now we can still do some algebra on this, and we'll need to. Now the advantage of where we stand now compared to where we were originally is that we could not, in this original form, combine the x with the square root of x plus 2. You just can't multiply within a root like that. Like, there'd be no way to distribute the x inside the root, and that's a problem to be able to integrate this. But where we are now after doing this substitution is such that I actually could distribute the square root of u, which is really u to the 1/2, inside these parentheses now. Mathematically it works fine, which means we really have the integral of, if I have u times the square root of u, that's like u times u to the 1/2, that would be u to the 3/2, minus 2 u to the 1/2 du. That's just distributing our square root of u in. Notice we have only the u variable, everything's lined up for that. Furthermore, this is an antiderivative we can do with our power rule. So we'll go ahead and rewrite this as u to the, we're going to add 1 to the power, so u to the 5 halves, but we have to divide by that new power of 5 halves as well. That's our first term, minus 2 u to the 3 halves over 3 halves plus c. Okay, let's go ahead and rewrite this now. But we have to go back in and simplify the fractions and then replace u. So this will end up being 2/5 if I flip the fraction upside down with the reciprocal. 2/5 times u, which is really x plus 2 originally there, to the 5 halves power, minus 4/3. Okay, now the 4/3 comes from flipping this 3 halves upside down as a reciprocal and combining it with the 2 that was already in front of it. So minus 4/3, and then it would be u to the 3 halves, but remember u is really x plus 2, so x plus 2 to the 3 halves, and then we'll say plus c. And there we have our final antiderivative for this function. Recall that as is always the case with an antiderivative here, you could actually check your work on these by taking a derivative, and you should get the original integrand of this function when you do. It's just a good way to check some work. Sometimes it's at least as much time to do that, but it's not a bad choice if you want to be more secure about your results. Our next example is the integral of, we have a fraction here where the numerator is the cosine of pi over x, and the denominator is x squared, and this is all dx. Now remember, we're looking to simplify this with a substitution wherein we let u equal something, some part of this function whose derivative is also part of this function, perhaps off by a constant. So it may be a little less obvious in this case, unless you're really familiar with all your derivatives here, but let's let u equal pi over x, because then du dx will end up being negative pi over x squared. If we multiply both sides by dx, we'll end up with du, and not only that, but divide by negative, so we'll say negative du equals pi over x squared dx, but notice the pi as a constant is not a constant in our original integrand either, so we'll divide both sides by pi and make this really a negative 1 over pi. Du on the left side equals 1 over x squared dx. Now we can replace the 1 over x squared and dx with those pieces in our original integrand, which leaves cosine of u above it, which means everything is represented. So let's rewrite this integral as the integral of, I'm going to put the constant of negative 1 over pi out in front that we already discussed. We'll put our du at the end. Everything else is represented, so we'll just write it as cosine of u. And then we'll take the antiderivative, keeping the constant out front, so negative 1 over pi. The antiderivative of cosine is sine, so we'll have sine of u, and then plus c. Now, of course, we'll go back in and replace u with what we know it is for a final result of negative 1 over pi times the sine of pi over x plus c. For our next example, we have the integral of, it's a fraction where the numerator is 2 to the t and the denominator is 2 to the t plus 3. Now we want to use a substitution to simplify this. We want to let u equal some part of this function whose derivative is also part of this function, perhaps off by a constant. Furthermore, we'd like to simplify the function as much as possible in the substitution process. So let's go ahead and let u equal the more complicated looking denominator here, which is 2 to the t plus 3. That means du dt, if you recall our exponential derivatives, will end up being 2 to the t times the natural log of 2. Now let's do two steps to this at once here, noticing that we have this natural log of 2, which is actually a constant, and we don't have that constant in our original. So remember, we can be off by a constant and fix it with not too much trouble. And let's also multiply both sides by dt. So this will give us 1 over the natural log of 2 du on the left side after dividing by natural log of 2 on both sides equals 2 to the t dt on the right after multiplying by dt on both sides. The good news is that the 2 to the t dt will actually replace key parts of our original integrand, and the rest of it we can use simply as a constant or the u replacement. So let's rewrite this as the integral of, I'm going to put the 1 over natural log of 2, that's our constant. I'm going to put it out front like we've been doing. And then afterward we're going to have the du, I'll just put that near the end. Okay, and then in between, notice the 2 to the t dt is what just got replaced with those two items. The only thing left would be then 1 over u. So this equals 1 over the natural log of 2, that's our constant here, times the natural log of the absolute value of u, that's our antiderivative there, plus c. So now let's go ahead and replace things. This is 1 over the natural log of 2 times the natural log of the absolute value of 2 to the t plus 3 plus c. Now, in this case, with the absolute value, what's inside of it is 2 to the t plus 3, and that's actually only positive. 2 to the t is an exponential that's only positive. If you add 3, it's still only positive. So you may see this kind of result written without the absolute value sign, since it's guaranteed to be positive. So you could see it as 1 over the natural log of 2 times the natural log of 2 to the t plus 3 in parentheses instead of absolute value, since it really is the same thing. Our next example is the integral of, it's a fraction where the numerator is simply dt and the denominator is cosine squared of t times the square root of 1 plus tangent of t. Usually you'll see the dt at the end of the integrand, but here it's written in the numerator. It's the same thing. You could write it at the end and just put a 1 in the numerator. Either way, this is what we have. We're looking to use a substitution to make this better, and we want to let u be some part of the function whose derivative is also part of the function. Look carefully at this and find that if we could let u equal what's inside the square root, that would be 1 plus tangent of t. If you think ahead a step or two, the derivative of tangent is secant squared. You may say, well, we don't have that as part of our function. Well, actually we do. This cosine squared in the denominator, that's really a 1 over cosine squared, which is really a secant squared. So it is kind of lurking here, but disguised a bit. Let's go ahead and take a step by taking the derivative and say du dt of our u equation here is going to be secant squared of t. If I multiply both sides by dt, I could rewrite this as follows. Du equals secant squared of t dt. Now remember, secant squared is really 1 over cosine squared. Therefore, this secant squared t dt actually does replace both items in our original here, this dt over cosine squared of t. Those are the same thing. So let's restart this integral as du, which is replacing the dt over cosine squared of t as we just said, which means all we have left is 1 over the square root of u. That will rewrite as 1 over u to the 1/2 du, which is really, if we kind of back up and start over here, that's really the same thing as the integral of u to the negative 1/2 du. Now we can do our antiderivative rule and make that u to the positive 1/2 over 1/2 plus c. This is really the same thing as 2. If you flip the 1/2 up and over, 2 times the square root, which is the u to the 1/2 here, but instead of u, we're going to go back and replace it with 1 plus tangent of t, and then of course we'll put our plus c for our final result. Our next example is the integral of, it's a fraction where the numerator is the cosine of the natural log of t, and the denominator is just t. Now if we look carefully, we'll find that if we let u equal the natural log of t, which is the input of this cosine part of our integrand, then it'll work out, I think, conveniently, because du, as you may recall, would be 1 over t dt. Well, that's an exact match for two key pieces of our integrand. If we rewrite this then as the cosine of u du, we can do so with confidence, knowing that the 1 over t dt is replacing both of those items, and then the cosine of u is representing the rest. If we go ahead and then with an antiderivative of cosine would be sine, so we have sine of u plus c. Of course, then we'll just replace u with what it is. So we really have sine of the natural log of t plus c. Our next example is the integral of, it's a fraction, where the numerator is x and the denominator is 1 plus x to the fourth. Now what we've been doing with our substitutions is trying to let u equal some part of the integrand function whose derivative is also part of the function. The problem with this one is, if you try to do that, it seems like it comes up short. If you let u equal the denominator 1 plus x to the fourth, the derivative of that would be 4x cubed, but we don't have an x cubed, we have just an x in the numerator here, so it wouldn't be a direct replacement. So for this one, we're going to take a slightly different route, and we're actually going to envision this as something different. If I imagine this as the integral of x over 1 plus x squared squared dx, okay, that's equivalent. I know you may say, well, I wouldn't have thought of that. Okay, I know, but now you're seeing it, and at least then you'll be able to spot it again and use this as necessary. But in this way, if I let u equal x squared, which is what's inside the parentheses in this rewrite, then it'll work out because du will be 2x dx, or we could say 1/2 du equals x dx. And now we have the x dx replacement we were hoping for here. Furthermore, we could rewrite this as the integral of, so x dx are gone, that's just the du replacing it, the 1/2 should be out front, we'll put the du at the end, and then really this is 1 over 1 plus u squared, since we let u be this x squared. Conveniently now you may recall that this is actually one of our inverse trig derivatives here. So the antiderivative would end up being 1/2 times, this would be tangent inverse, or you could say arctan, same thing, tangent inverse of u plus c. So let's rewrite this as 1/2 tangent inverse of, instead of u, we'll put x squared plus c. Our next example is the integral of x squared times the square root of 2 plus x, and then that's all dx. Now, you'll recall we've seen something like this in the past examples here, where, remember how we had something like this where you can't distribute the x squared into the root, it just doesn't work. Algebraically, you can't distribute inside a square root. So you may recall we had a way to get around this, and we're going to have to do the same kind of thing here. So let's go ahead and let u equal what's inside the root, which is 2 plus x, or x plus 2, same thing. And then, of course, you'll notice or recall that this is a trivial derivative. We just get du equals dx, or 1 dx, you could say. But then, as we did before, we're going to go ahead and take our u equation and solve it for x, which will help us out here. If I rewrite this as x equals u minus 2, then I'll be able to replace the x squared that I have in the integrand by utilizing this other version of our u equation. So let's rewrite a new integral here, but instead of x squared, I'm going to write this as u minus 2 squared, and then we have the square root of u du. Okay, so like we saw before as well, this is really u to the 1/2, the square root of u, and then we'll expand this u minus 2 squared. If you just kind of FOIL that out, you'll end up with u squared minus 4u plus 4, and then we have that still times this u to the 1/2 du. But now, the whole point of doing all this is that now I actually could distribute this u to the 1/2 inside. So let's go back and kind of restart. where we'll get the integral of u to the 5 halves minus 4u to the 3 halves plus 4u to the 1 half du. So we haven't even done our integral yet. We're just kind of rearranging everything, getting it all set up. Doing antiderivatives term by term now in our integrand, which has several just power terms, will give us 2u to the 7 halves over 7 minus 8u to the 5 halves over 5. Okay, so I'm skipping a step or two of arithmetic here, but it's just you're increasing the power and dividing by the new power, and then I'm also simplifying the fractions in the process. And then we'll have plus 8u to the 3 halves over 3, and then of course plus c. And remember, we want to replace these u's with what we had originally set it equal to, so we'll end up with 2 times, it's 2 plus x, I'll leave it the same way here, 2 plus x to the 7 halves over 7 minus 8 times 2 plus x to the 5 halves over 5 plus 8 times 2 plus x to the 3 halves over 3, and then plus, don't forget our plus c out of space. Okay, we'll put it in there at the end. So this ultimately is our result for this one. Okay, one more example. If you stuck with it this long, hopefully you've learned a lot. But this next example is another key one. It's the integral of x cubed times the square root of x squared plus 1 dx. Now, as we've been doing, we want to let u equal some part of this function whose derivative is also part of it, and also simplify the function in the process. Now, you may say, well, let's let u be the inside of the square root, because we've done that a few times. Okay, not bad, but if I do that, x squared plus 1, of course you can anticipate the derivative of that being 2x, and that's not quite part of our original integrand here. So we're going to do another little trick on this one and rewrite it, but in the process we're going to split something up. Remember this x cubed we had originally? I'm going to split that to be just an x squared times the square root of x squared plus 1, and then I'm going to put another one of those x's actually at the end. So I'm splitting x cubed into x squared times x, but I'm also separating the x squared and the x that I just mentioned. It's just for convenience, okay? So let's see how this all works out. If I take my u equation and take its derivative, I'll end up with then du equals 2x dx. Of course, that could be written as 1/2 du equals x dx. And now you're finally seeing the motivation for this split, right? So the x dx is now showing up, and we had split the x cubed in a way that gave us the x dx. That'll be replaceable. The 1/2 du is fine, it's just a constant, and then the du will show up as our variable of integration. We will also need, though, a way to solve this original u equation for x squared, since we have one of those to replace as well. So this will turn out to mean that x squared equals u minus 1. So now we can replace this all as u minus 1, that's going in for the x squared, times the square root of u du. But now algebraically, as we've seen before, it's actually possible to distribute this square root of u inside the parentheses now, which was not possible originally. Of course, the square root of u is really just u to the 1/2. So we really have the integral of u to the 3 halves minus u to the 1/2 if we distribute that square root of u inside. Let's also not forget our constant of 1/2. That should be written out in front, that we had gotten in our substitution. And so here we go with something that we can integrate quite nicely. It's just a power function set here. So this will turn out to be 1/2 times u to the 5 halves over 5 halves minus u to the 3 halves over 3 halves plus c. But then we could actually simplify the 1/2 would cancel with all these 1/2s that are in the denominator. If that step of algebra is troublesome. You could write it out in a few more steps to be super duper clear about it, but those will cancel. And then if we replace u with what we had said it was, we end up with a final answer of x squared plus 1 to the 5 halves all over 5 minus x squared plus 1 to the 3 halves all over 3 plus c. And this will be our final result.